General Physics 2 is brought to you by Physics Classroom. This lesson shall provide understanding on how we can determine the electrostatic force by using Coulomb's law. Like charges repel each other, while unlike charges attract each other. If the charges are at rest, then the force between them is known as the electrostatic force. The electrostatic force between charges increases when the magnitude of the charges increases, or the distance between the charges decreases. The electrostatic force was first studied in detail by Charles Augustin de Coulomb around 1784. Coulomb's law states that the magnitude of the electrostatic force between two-point charges is directly proportional to the product of the magnitudes of the charges, and inversely proportional to the square of the distance between them. The proportionality constant K is called the electrostatic constant and has the value 9.0 times 10 to the 9 Newton meter squared per Coulomb squared in free space. Notice how similar in form Coulomb's law is to Newton's universal law of gravitation between two-point-like particles. m1 and m2 are the masses of the two-point-like particles, d is the distance between them, and g is the gravitational constant. Both are inverse square laws. To further illustrate the application of Coulomb's law, let us now consider this illustrative problem number 1. Two-point-like charges carrying charges of positive 3.0 nanocoulomb and negative 5.0 nanocoulomb are 2.0 meters apart. Determine the magnitude of the electrostatic force between them, and state whether it is attractive or repulsive. Note that 1 nanocoulomb equals 1 times 10 to the negative 9 coulomb. We can draw a diagram of the situation. The positive charge Q1 is on the right direction. The negative charge Q2 is on the left direction. And the distance between the two charges is 2 meters. The given quantities are the magnitude of the charges Q1 and Q2 equal to positive 3 nanocoulomb and negative 5 nanocoulomb respectively. The distance r equals 2 meters, and the electrostatic constant K equals 9 times 10 to the 9 Newton meter squared per Coulomb squared. The required quantity is the electrostatic force, and the solution can be done by substituting all the given values to the formula, F equals K times Q1 times Q2, all over r squared. We get F equals 3.38 times 10 to the negative 8 Newton. We can draw a free body diagram to show the forces. Each charge experiences a force with the same magnitude and the forces are attractive. And here's illustrative problem number 2. 3-point charges are in a straight line. Their charges are Q1 equals positive 2 times 10 to the negative 9 coulomb. Q2 equals positive 1 times 10 to the negative 9 coulomb. Q3 equals negative 3 times 10 to the negative 9 coulomb. The distance between Q1 and Q2 is 2 times 10 to the negative 2 meters, and the distance between Q2 and Q3 is 4 times 10 to the negative 2 meters. What is the net electrostatic force on Q2 due to the other two charges? We can draw a diagram of the situation. In the diagram, Q1 and Q2 are like charges, which are 2 times 10 to the negative 2 meters apart. On the other side, Q2 and Q3 are unlike charges, which are 4 times 10 to the negative 2 meters apart. For the solution, let us first calculate the magnitude of the forces. Letter A. Force on Q2, due to Q1. By substituting the given values of the electrostatic constant, charges Q1 and Q2, and the distance between the two charges, to the Coulomb's law formula, we get the repulsive electrostatic force F, equal to 4.5 times 10 to the negative 5 Newton. Letter B. Force on Q sub 2, due to Q sub 3. By substituting the given values of the electrostatic constant, charges Q sub 2, and Q sub 3, and the distance between the two charges, to the Coulomb's law formula, we get the attractive electrostatic force F, equal to 1.69 times 10 to the negative 5 Newton. The second step is the vector addition of forces. The force between Q sub 1 and Q sub 2 is repulsive, because they are like charges. This means that Q sub 1 pushes Q sub 2 to the right, or in the positive direction. The force between Q sub 2 and Q sub 3 is attractive, because they are unlike charges, and pulls Q sub 2 to the right. Therefore, both forces are acting in the positive direction. So we have to add F sub 1, equal to 4.5 times 10 to the negative 5 Newton, and F sub 2, equal to 1.69 times 10 to the negative 5 Newton. Thus the resultant force acting on Q sub 2 is 6.19 times 10 to the negative 5 Newton to the right. And here's your second performance task. Solve the problems below. Number 1. A pith ball is a small light ball that can easily be charged. What is the magnitude of the repulsive force between two pith balls that are 8 centimeters apart and have equal charges of negative 30 nanocoulomb? Number 2. How strong is the attractive force between a glass rod with a 0.7 microcoulomb charge and a silk cloth with a negative 0.6 microcoulomb charge, which are 12 centimeters apart, using the approximation that they act like point charges? Number 3. For the charge configuration shown below, calculate the resultant force on Q sub 2. If Q sub 1 equals 2.3 times 10 to the negative 7 coulomb, Q sub 2 equals 4 times 10 to the negative 6 coulomb, Q sub 3 equals 3.3 times 10 to the negative 7 coulomb, R sub 1 equals 2.5 times 10 to the negative 1 meter, R sub 2 equals 3.7 times 10 to the negative 2 meter. Thank you. Hope you had another electrifying but meaningful learning experience.